In this video, I would like to provide some clarity on how to understand what the transpose of a matrix is about. In my experience, explanations of the transpose tend to err toward one of two extremes, either explaining how to take the transpose while providing no real intuition for what this actually means, or providing so much detail with higher level math concepts that new students can't make any sense of it. So I'm aiming here for a middle ground that should give you a better idea of what the transpose is all about, but without getting bogged down in really abstract concepts. For this video, I'm going to assume that you understand how we can think of a matrix as a linear transformation of space, what a matrix inverse and the identity matrix are, and what a dot product of two vectors is. If you aren't familiar with these concepts or need a review, see the excellent video series on The Essence of Linear Algebra by 3 Blue 1 Brown. It would also be helpful if you know a bit about the singular value decomposition, but if not, don't worry about it, we'll go over what you need to know. So what is the transpose? You've probably learned before that to find the transpose of a matrix, you take that matrix and mirror reflect it over its diagonal. Elements on the diagonal stay put, while elements off the diagonal get swapped with their mirror on the other side. Square matrices stay the same shape when you take the transpose, but non-square matrices have their dimension flipped around. A few useful properties that come up a lot are: if you want the transpose of a sum of two matrices, you can distribute the transpose into the sum, and so take the transpose of the individual matrices and then add them up. Here's a little demonstration of that. If you want the transpose of the product of two matrices, you can distribute the transpose into the product, but you also have to flip the order of the product. If you take the transpose twice, so the transpose of the transpose, then this gets you back to where you started. That makes good sense because you're just doing the mirror flipping twice. If you take the transpose of the inverse of a matrix, you'll get the same result as if you swap the operation order, taking the inverse of the transpose of the matrix. Here's a quick proof of that. And lastly, we can represent a dot product of two column vectors by taking the transpose of the first vector and then doing standard matrix multiplication. Okay, but now let's think geometrically. So say we start off with some vector x in space. Then we do a linear transformation using the matrix A. Applying the matrix A to the vector x is going to give us some new vector which we'll call x bar. Let's do the same thing with another vector that we'll call v, and we'll call the result v bar. So here's our motivating question. Suppose that before we do the transformation, we take the dot product of v and x. And after we do the transformation, we take the dot product of the newly transformed vectors, v bar and x bar. The question we want to ask is, will we get the same number or a different number? Or in other words, do linear transformations preserve the dot product between two vectors? You might want to pause the video and think about that for a moment. Okay, the answer, it turns out, is only sometimes. Let's see that. First write v.x as v transpose x. And we can write v bar dot x bar as v bar transpose x bar. Next, remembering that v bar and x bar came to us from multiplying by a, let's write the transformed versions in terms of the original versions multiplied by a. Then distribute the transpose into the product. In order for the dot product of the transformed vectors to be the same as the dot product with the original vectors for any choice of vectors, we need for this term in the middle here, A transpose A, to not affect the calculation at all. In other words, we need for A transpose A to be the identity matrix. If it were, then we would have V transpose times the identity matrix times X, which would just give us V transpose X, the same as the original dot product. And in order for A transpose A to be the identity matrix, that would have to mean that A transpose is equal to A inverse. This is not true for plenty of matrices that we could have used as A, and therefore it will not in general be true that the dot product of the transformed vectors is the same as the dot product of the original vectors. So we have our answer. Linear transformations do not, in general, preserve the dot product. This actually makes pretty good sense visually. Remember that the value of the dot product is a function of the lengths of the two vectors and the angle between them. And linear transformations can stretch space in ways that change angles and also change lengths differently in different directions. For example, look at these two vectors, which are pointing in roughly the same direction, and so should have some positive number for their dot product. And next consider the transformation that shears space like this. Now the vectors are perpendicular, and perpendicular vectors always have a dot product of 0, so the dot product must have changed. But what if what we want to do is to preserve the dot product? That is, suppose we'd like to know two sets of vectors, one from before the transformation and one from after, such that both sets have the same dot product. This is what the transpose can do for us. So let's do this. We know that we can't multiply both x and v by a, so what if we multiply v by something else? Is there some other matrix that we can multiply by that will preserve the dot product? Well, let's try it and see. Call that matrix M, and let's see what M would have to be in order to preserve the dot product from before and after the multiplication. Similar logic as earlier gets you to the conclusion that, for this to work for any two vectors, then the transpose of M has to be equal to the inverse of A. And so M must be the transpose of the inverse of A. Great, so we've done it. If you want to keep the dot product the same before and after a matrix multiplication, then you might have to transform the vectors a bit differently. And if you transform the first vector using a matrix A, then the matrix that tells you how to transform the second vector is the transpose of the inverse of A. In the specific case that the inverse of A is also the transpose of A, then this just gives you back A. For a graphical example, if we take these two vectors here, then apply this transformation, we can see that the dot product changes a lot. The angles before and after are fairly similar, but both vectors have gotten longer. I'm going to reverse the transformation again, but now I'll leave the teal vector behind, which I'll indicate with a dash. That dashed teal vector is x bar. The A inverse-transpose matrix we derived earlier can now tell us what we have to transform V to keep the dot product the same. And that would be this vector here. I'll dash this one too, and then put the original vectors back on the screen non-dashed. So again, the point here is that the dot product of the solid vectors is equal to the dot product of the dashed vectors. As we said though, there are some transformations, like this one here, which just so happen to have their inverse equal to the transpose, in which case we can do the same transformation to both vectors, and the dot product stays the same before and after. Next, I want to try to give you some geometric intuition for what these transformations are doing. This can be difficult to do, but bear with me here. To start, let's look more at that special case, when the transpose of a matrix is the same as its inverse. This actually turns out to correspond to a special class of matrices called orthogonal matrices. We saw before that in this case, we can use the transformation A to transform both vectors, and the dot product won't change. So A is some transformation that on its own preserves dot products. Can you think of what kind of transformations this might be? Maybe pause the video to ponder that. Well, because the value of the dot product depends on the lengths and angles between vectors, it must be that the transformation preserves lengths and angles. So an example might be a reflection, like this one, or a rotation, like this. The key point is that they have no stretching or squishing of space, just rotation or reflection. Those are called orthogonal transformations. And because the transpose is the inverse, that means that for a reflection or rotation, doing the transformation given by the transpose will undo that original transformation. That's our first insight at what the transpose does geometrically, which is pretty nifty, and we're going to use it again in a moment, so remember that. To go deeper, we'll need another tool from linear algebra called the Singular Value Decomposition. I'm not going to go deep on this here, we'll just hit the headline, which is that you can break down any linear transformation into a combination of three parts. Those parts are a rotation or reflection, then a scaling of space at the axes, followed by another rotation or reflection. So that looks something like this. First, here's some linear transformation. Now let's undo that and watch it again broken into stages. I'm also going to add this circle to track the stretching. So first we do a rotation, then we stretch or squish at the axes, then we do a final rotation, and there we are, the same transformation as earlier. Because matrices represent linear transformations, and matrix multiplication represents applying transformations successively, what this means is that we can factor any matrix into three matrices, where the first one does the rotation, the second one does the stretching, and the third one does the final rotation. Note that the notation I'm using here is not standard. You'll more commonly see it written like this. But I like my version better, so indulge me. Also, I'm not going to explain how to actually calculate these things. All we need to know here is that it can be done. So let's go back to our forward transformation rule, which looked like this. If we now represent A by its SVD factorization, then look what we get for A inverse transpose. We can distribute the inverse into the parentheses if we reverse the order of the multiplication. When we distribute the transpose, we're going to keep in mind some important facts about the SVD matrices. First, because sigma is a matrix that stretches along the axes, it's actually a diagonal matrix, meaning it has entries only along the diagonal and the rest are zero. When we take the transpose of a diagonal matrix, we actually just get the same matrix back. So taking the transpose of sigma would just give us sigma. Because the inverse of a diagonal matrix is also a diagonal matrix, this is going to be true for sigma inverse too. Its transpose is just sigma inverse. For the R's, on the other hand, these are pure rotations or reflections, i.e. they are orthogonal matrices. And like we said before, for orthogonal matrices, its transpose is its inverse, which means that the transpose of the inverse is just the original rotation. So now we're ready to distribute that transpose, and the result is this. And I encourage you to stop and try to appreciate what a nice result this is. It says, if we transform x according to some rotation, scaling, then rotation, and our goal is to preserve the dot product, then we have to transform v according to the same first rotation, then the inverse scaling, then the same final rotation. Let's take a look at that geometrically. Here's the same vector x and transformation we've looked at already. Now let's undo that and look at the decomposition of that transformation, which consists of a rotation, then a scaling at the axes, then another rotation. I'm going to restore here, but leave our x bar vector behind. Now let's see the v vector and figure out what we have to do to get v bar. We do the same first rotation as before, but then the inverse scaling, and then the same final rotation. And now if you'll indulge me just a little bit, I want to show you both of those at the same time. Come on, tell me that isn't delightful. Let me just show you some more examples. While you watch this time, I'd like you to think about what happens to the dot product between the two vectors during each one of these steps. In an orthogonal transformation, like a rotation, the dot product is preserved, so the first step doesn't affect it at all. In the scaling step, because the components of V are being scaled in the exact opposite proportion as the components of X, the dot product remains unchanged, which, come on, that's awesome. And then the final step is another orthogonal transformation, which again leaves the dot product unchanged. And that's how we get our invariant dot product. Here's one last example. The thing that's new this time is that both of the scaling factors, which are called singular values by the way, are greater than 1. Because of that, the circle grows in size in both directions. And so in the inverse-transpose transform, it shrinks in both directions. I said this video was about understanding what the transpose of a matrix does, and so you might be wondering, are we ever actually going to get to that? Okay, fair. To get us there, you might also be noticing that our formula of multiplying V by the transpose of the inverse of A seems to depend on A being invertible. And if you think about it, that should make you uneasy. After all, even if A is not invertible, you can still take the dot products of vectors before and after the transformation. So how can we generalize all this to the case when A isn't invertible? The answer is that we'll have to make a little mental shift. So we have a set of vectors in the untransformed or input space, which are x and v, and we have another set of vectors in the transformed or output space, which are x bar and v bar. Now, before we picked two arbitrary vectors in the input space, and then picked a rule to transform them, and that gave us the new vectors in the output space. We're going to keep doing that for x, but now for v, I'd like you to shift your mindset a little. Instead of picking a vector v in the input space, we're going to pick a vector v bar in the output space. And then we'll use a rule to get from there to a vector v in the input space. This may be a bit confusing, so pause and think about that if need be, but it doesn't change all that much ultimately. We still have two sets of two vectors, and for each set we pick only one vector, then use some rule to find the other. To do that, let's solve this equation for v, to get v equals A transpose v bar. And now we're finally looking square on at the transpose of A. And the equation that represents this whole lesson looks like this. I definitely encourage you to pause the video and take in this equation a bit. Same as before, on the left side is a dot product in the input space, and the right side is a dot product in the output space, and to transform x between input and output, we'll use A, and to transform v from output to input, we use A transpose. I will say though that the bar here over the v is not standard, and so in the wild you might encounter an equation that looks more like this. But I like the bars, so I'm going to put them back. Anyway, that all looks something like this. We'll start again with our vector x, and then we'll multiply by A to get our x bar, the dashed vector. But now we'll pick a vector v bar and multiply by A transpose to get the vector v. What the transpose does for us here is that it ensures that the dot product of the vectors x and v is the same as the dot product of x bar and v bar. So people often ask if the transpose of a matrix is like its inverse, and we can see here that it does have a sort of inverse-y quality to it. For one thing, it does transform back from the output space to the input space of the original transformation. This is especially easy to see for non-square matrices, since the dimensions get swapped. So, for example, if the original transformation goes from 3-dimensional space to 2-dimensional space, then the transpose is a transformation from 2-dimensional space to 3-dimensional space. But as before, it is not necessarily the same as the inverse, and we can also see this nicely with non-square matrices. If our original transformation goes from 3 dimensions to 2 dimensions, then that won't be invertible, because we're losing all that information from the 3rd dimension. But it will still have a transpose. To make sense of the transpose by itself geometrically, I'd go back to the singular value decomposition. We saw before that the transpose of the inverse preserves dot products in the forward direction by doing the same initial rotation as A, then the inverse scaling, then the same final rotation. Fairly logically, we can think of the inverse of A as just doing everything in reverse. It reverses the final rotation, then reverses the scaling, then reverses the initial rotation. Maybe pause the video here and see if you can figure out what the form of A transpose should be. Since the same relationships should hold for the pair of equations on the right as the pair on the left, a little logic tells us that it must look like this. We can see that A transpose first reverses the final rotation, then does the same scaling as A, and then reverses the initial rotation. So let's see it. Here on the screen is the forward transformation A we're looking at, doing a rotation, then a scaling, then a rotation. Looking at the inverse of A first, that would just reverse the second rotation, then reverse the scaling, then reverse the first rotation. Now the transpose of the inverse of A is going to do the same initial rotation, but then the reverse scaling, and then the same final rotation. And finally, the transpose of A is going to undo the second rotation, but then do the same scaling as A, but then undo the first rotation. Just for fun now, let's reset and see a few of those at the same time. First, the forward transformations. Now the backward transformations. For the case when A isn't invertible, then sigma won't be invertible either, so we can't use these two formulas. So we're left with A to transform in the forward direction, and A transpose to transform in the backward direction. As a final aside, I want to briefly mention a special case. This is when the second rotation happens to be just the reverse of the first rotation, which we might as well just call R. So then we can think of the matrix as doing a rotation, then scaling, then undoing the rotation. If we take a look at the form of the transpose for this case, and make the same substitutions, you'll notice that it ends up having the exact same form. So what we have here is that the matrix is equal to its own transpose. For matrices like these, when you flip elements over the diagonal in order to take the transpose, you get back the same thing you started with. For that reason, these are called symmetric matrices, since they're symmetric about the matrix's diagonal. Here's an example. So I'm going to stop there. To summarize, linear transformations do not, in general, preserve the dot product of vectors. The exception to this are orthogonal transformations, which are pure rotations or reflections, where the transpose of the matrix is equal to its inverse. But otherwise, to maintain the dot product, if we transform one of the vectors in the input space by some transformation A, then we'll need to transform the other input vector by A inverse transpose. Alternatively, we can pick a vector in the output space and transform it to one in the input space by using A transpose. And we'll have to do this if A isn't invertible. So the transpose of A is a different transformation, but which goes from the output space to the input space, and helps us preserve the dot product in both spaces. We saw this visually and looked at the singular value decomposition of all the transformations involved to see just how it is that they preserve the dot product. Hopefully this gives you a bit better understanding of what the transpose means, but without muddying the waters too much. If you want to go way deeper on these topics, then you can, and I'll leave some links in the description. Thanks for watching!